People joining in. That's good. Folks, we'll be starting in a minute. People joining in, and we are live. So that's good. All set. So I can see the recording is on, live is on. Praneet, off to you, but we can start in a minute.
Okay, thanks, Rahul. All right, I see people joining in still, but I think in the interest of time, we can start with today's presentations. What do you say, Dhruv?
Yeah, Praneet, you can start whenever you are ready.
Hi, everyone. Welcome to the day 4 of Connections 22. This is our flagship event, as you might already know. And today we are going to be doing the IoT track, which is also my personal favorite because I've been involved with IoT ever since I started working. And this event is in collaboration with IISOC and INTC. Thanks, INTC, for helping us out this time and collaborating with us. This is the Ietf 113 Post Ietf Forum. And today we have a lot of interesting speakers and some very interesting panels. So we'll be starting with Carsten. And Carsten will be talking about the standard IoT standards landscape with us for about 45 minutes. And then we have the IoT webinar series Kickoff, where Pascal and Georgios will be presenting some of their work to us. Finally, we'll end with a very interesting panel discussion on IoT led by Shwetha and some of very prominent people in the IoT world. Next slide, please. And as we all know, we are always thankful to our sponsors, and today we wouldn't be here without them. So a great thank you to all of the sponsors from all of us here at INTC and IISOC. Thanks to Cisco, APNEC, Internet Society, and Juniper Networks for sponsoring us for this event. Now, some ground housekeeping rules. So, as always, we motivate people to ask questions. We are very much welcome when it comes to questions. Feel free to ask your questions in the Q&A box, and if there are any other discussions, please follow them on the chat. And we want an engaging discussion, and we very much motivate people to join. So please ask your questions. And while if you want to talk while a presentation is going on, if you want to ask your question live, you can be unmuted and you can mention your name and start asking your question, very much like the IETF way. One of our panelists can mark you down and unmute you if you wish to speak yourselves, or you can do so yourself also. And as I said before, please use the Zoom chat for other discussions and only Q&A when you want to ask your question to our host or panelist or the speakers. And finally, this time, as you might have been hearing on all other 3 days, we have a prize for the best question of the day. This is just to promote the audience participation because we encourage questions more than anything, and we very much love engaging discussions. So the best question for the day is going to win a gift, which is a donation to their recommended charity or cause. This thing will be announcing at the end of Connections, but yes, please engage. We have a best question prize at the end. Finally, now without further ado, I would like to kick off today's sessions with Carsten. And today we are starting off with the standards landscape at the Ietf. And here we'll be basically talking about how the IoT landscape has evolved over the years. For this, there couldn't be a better person than Carsten himself because he has been involved with IoT and with Ietf even before I was born, I guess. So yeah, that's here. We are very much grateful to Carsten for giving us his precious time. And a little bit about Carsten now. Carsten is working as an honorary professor at the Internet Technology University Bremen, and he is a member for the Center of Computing and Communications Technology. He has been involved with IETF in chartering and initiating a lot of working groups related to IoT, such as the Core, the CoApp working group, and initially the T2TRG, Things to Things Research Group. So I would like to say this again. I know I've said it often, but please ask your questions. You wouldn't find a better person than Carsten for answering your IoT questions. I don't think I can do justice to Carsten's intro because he's done so much that there isn't enough time to say. So Carsten, would you please like to briefly introduce yourself and kick off the session?
Thank you. So thank you for the kind words in the introduction. I hope you can see my slides. No, you can't.
Yes, we see them now.
So now you should be able to see my slides. My computer is pretty heavy in processing right now. I don't know if you hear the fan. That's weird. Okay, so each time you run a Zoom conference, it works differently. So I want to quickly talk about the IETF standards landscape for the Internet of Things. And clearly that's not something you can do at all within 1 hour. So I will be pretty brief in many places. And you can download the slides from slides.cabo.space if you want to follow me in some places where I will be showing a slide for 5 seconds or so. So who am I? I'm a honorary professor at the Universität Bremen in Germany. In the IETF, I am now again chairing the core working group. I tried to get rid of that job after 10 years, but for some reason they needed me again. And also chairing the Think2Think research group in the IRTF. So there was a bio on the slide that Praneet had, but I have a short abbreviated bio. So that's RFCs I have been co-authoring, and there are a few in light gray which are in the RFC editor queue right now, and there's even a 50th one down there. So I've been trying to get documents out there that help us standardize the internet. So let me say this in other words. So what I'm really have been doing since the late 1980s was bringing the internet to new applications. And that always works like this. We start in a situation where everybody who really knows anything is going to tell me that application X will never run on the internet. And then it takes a while and another while. And then people ask me, how do we turn off the remaining parts of X that still aren't on the internet? So that has been the overall theme of my work since the late 1980s, and IoT was no change. Now, what's interesting about the IoT? This is a slide from Ericsson that really shows what's going on for the first 150 years in the history of Ericsson. Most of the time they spent with connecting places. to classical phone networks. Then at some point we started connecting people. And what we have now started to do is connecting things. So as you can see, the numbers are getting larger. While there may be 1 billion or so places that need to be connected, there are 5 billions. That's the number for an engineer. The reality, of course, is 8 billion people. And there are at least an order of magnitude more things, probably way more than that. And that's interesting because one of the major aspects of the internet was that it is about scaling. We needed to be able to scale up the internet for the last 25 years, and that's probably not going to change. And scaling up also is a theme in the Internet of Things. So the number of nodes goes up. Oh, this still says 2020. I should probably update that slide. But what's interesting here is we are not just able to talk about scaling up, we also have to talk about scaling down. Because if we have a number of nodes that actually is getting close to 1 trillion, then we have to make sure that these nodes don't consume all of our resources. So we cannot really scale things up without scaling things down. And this is about cost. This also is about complexity because we have to keep the system running, even with this really large number of nodes. And this also means that we have to go down in power usage as well. And that means we actually are learning a few words again that we haven't been using a lot, like kilobytes and megahertz, or even cent for the amount of money we want to spend on something. So a lot of the things we take for granted in the big internet do not necessarily apply in the Internet of Things. Let me just give you an example. This is from RFC 7228. Which we wrote to actually nail down some of these numbers a little bit, so we had it easier when discussing these things. The nodes, the smallest nodes that we reasonably can connect to the internet have about 10 kilobytes of data space and 100 kilobytes of code space. So we call that class 1 devices in RFC 7228. And this is pretty small compared to other systems that we are using every day. So our smartphones, of course, are several orders of magnitude larger in data, in code, but also in power usage. We have to recharge them every night, and they are in the watt range and not in the milliwatt or microwatt space that we actually need for the Internet of Things. So what we are essentially doing is well, this is just one class, of course. There are other classes as well. What we are essentially doing is the kind of computer that I started work with in the 1970s. These were about that size. So well, physically, of course, they were much larger, but they also had some 2-digit number of kilobytes. And so on. And we are just working on getting that functionality in a very small chip with very small power usage. So since the roots of the internet go back in the 70s, that's not necessarily a problem. We can make this work. But first of all, we have to adjust our expectations a little bit. And one interesting observation is that in the constrained node network space, Moore's law is less powerful than in other places, because if we get gains from Moore's law, at least from that part that is still left of Moore's law, we are going to use these gains to save power and to save cost, and not necessarily to increase the functionality of the system. And that has led to a very slow growth of performance, ROM and RAM parameters. Of course, they do grow, but we cannot just do what we have been doing in the desktop and server spaces. Just wait for next year's systems and they will be twice as fast and twice as large. So out of these constrained nodes, we build constrained networks. And the networks are mostly constrained because the nodes are constrained. So nodes need to sleep a lot to go down to microwatt powers. They probably only have a few hundred kilobits per second of data rate, and that's the total data rate for the entire network. They may use an unstable radio environment. They may be limited in packet size, and so on. So the kinds of networks that we're talking about are the Zigbee style networks, Bluetooth, Z-Wave, DEC ULE, and so on. And from the constrained nodes and the constrained networks that are able to accommodate these constrained nodes, we build constrained node networks. So this is essentially what I'm going to talk about today. Not because every single IoT device has to be constrained. That's obviously not the case. If you think about a car, that's also a kind of an IoT device, but a much more powerful one and also a much more expensive one. But the interesting thing about IoT is that it really needs to accommodate those very constrained nodes to be a complete network. And now, as I started out to say, we do want to use IP. So just as IP telephony completely has consumed the traditional telephony with its much more simple devices, the Internet of Things is consuming a lot of the existing systems that now can actually make use of functionality that only IP actually can provide. There is a flip side to that, because saying IP might sound like I'm saying the first 10,000 RFCs all need to be implemented or something like that. So there's lots of baggage that comes with talking about IP. And the fact that we can move systems to IP doesn't necessarily mean that we want to do that, and particularly that we want to incur all of the baggage. I have a very nice slide I can't show you because I don't have the image rights. The slide shows somebody on an autobahn on a motorcycle transporting a sofa. And that is obviously existence proof that you can transport sofas on motorcycles. But you may not want to. And even more interesting, being able to transport a sofa is not necessarily what should be guiding your decision on what motorcycle to buy. So for those very much scaled down systems, we probably want to make design decisions that also fit this aspect of scaling down. So when you are in a field like this, you run into two kinds of people. One is going to tell you IP is too expensive, and we have to do something simpler than IP. And the other ones are going to tell you, well, IP already works as it is, and there's nothing we need to do. And both groups are right in their own way. But what we have been trying to do actually is moving boundaries. So if you look at this graphics here, this shows linear space of complexity. So low complexity is left, high complexity is right. So complexity includes things like energy needs, cost, and so on. And the vertical axis is supposed to be the number of applications and the number of systems that we actually can support. And when you look at the complexity dimension, of course, on the right side, at some point, we simply can use Linux, and we essentially have a system that is not much different from your standard desktop or smartphone system. So anything that's being done with a Raspberry Pi is on right side of that complexity dimension. And then when we go down in complexity, we probably can down a little bit. We don't really need Linux to support internet technologies. We probably can do something that is a little bit more frugal. Linux systems are usually in the watt space. Maybe we can go into the milliwatt space. And there are some applications that can use internet technologies unchanged. And finally, there are some applications where we need to dial down the complexity even more. So we actually still can use internet technologies, but not necessarily in the same configurations we use them on the big systems. So the point of the work that we are doing here is moving this boundary to the left. And we can't move it a lot. We can move it a little bit. But that little bit is actually interesting when you think about the number of applications that you actually can run. That becomes much, much larger the further left you get on the complexity dimension. And if you look at the area behind this graph, that's actually quite sizable. So we have essentially in this graph doubled the number of applications we can run on the IoT. There are many ways this can be done. So in some cases, we can fix protocols. So for instance, the IPv6 neighbor discovery protocol was modified to become the 6LoWPAN neighbor discovery protocol. Sometimes we can just reuse protocols after removing some sources of complexity. And sometimes we can reuse architectures, but actually have to design protocols working within this architecture that are more appropriate for low complexity. So this is something that the Ietf has been working on forever, one might say. SNMP certainly was something that was done to reduce complexity of other management protocols that were being proposed. But specifically for IoT, the Ietf has been doing this for almost 20 years now, since 2005. And I want to go a little bit through the various activities in the Ietf. And of course, I should include the standard disclaimer that's actually true for the whole week, but let me just say that again. Nobody really speaks for the Ietf. Even the Ietf chair has to be very controlled in what he actually says about the Ietf, because the Ietf really is a collection of consensus processes. And these, of course, have diverse results, and nobody can fully predict what these consensus processes will produce. And there are even some additional processes like managing liaisons and so on. So the Ietf contains a lot of people who are interested in progressing the Internet of Things. These have different ideas. And what I'm going to try is bring my perspective in here, which may be a bit different from the perspectives of other people. Anyway, so since 2005, the Ietf has created 16 working groups. The Ietf work is split into areas, which are in turn split into working groups. And we have created 16 of these, and 2 of them have already been closed down, and probably the 6LoWPAN and the DICE working group, because they were just done with what they set out to do. Other working groups are still there, but might also be closed down or even reopened when it turns out there are new aspects that the working group would be good to have around for. So these working groups are structured in areas. Int is the internet area. So this is really about keeping your packets flowing. So what are the packet encapsulations? What are the forwarding decisions? How do you map to lower layer protocols? There is a routing area, which is interested in routing protocols. There is an application area. Well, the area is now called applications and real time, but it's really the applications aspect that is interesting here. There is a security area, and you can see from the size of that, of the number of working groups in the security area, that there's a lot to do in the security area. And finally, there's an operational area, and we are starting to pay more attention to the issues of running significant IoT networks. And besides the Ietf, of course, there's also the IRTF that has the thing-to-thing research group. So I have about 30 minutes for 16 working groups. That's, of course, going to be pretty limited in what I can say. So I will leave out some, and some I will only describe on a single slide. But maybe an important working group to look at is the 6LoWPAN working group. That was the first IoT working group that the Ietf created in 2005. And the idea was to make IPv6 available over these energy-saving, low-power, wireless personal area networks, 802.15.4. So we did the usual thing. We defined an encapsulation for IPv6, but then we had to do two things that are a bit unusual for someone just trying to run IP over something, which is we had to work on header compression and we had to work on network architecture. And why is that so? Of course, we have to work on header compression because IPv6 headers are about as large as the packets that you would often, as the entire packets that you often would find in an IoT environment. So these need to be compressed. And it turns out IPv6 packets can be compressed very well. So that's one RFC that was created here. And the other one was about network architecture, making sure this network can be set up in a way that reduces the complexity of that. So there were a few breakthroughs here. Well, one is, of course, the encapsulation, which it may be a little bit boring, but there is fragmentation in there. But more interesting for the header compression, a new concept was defined, the area text state. So there is state that actually applies to a whole area, to a whole 6LoWPAN. So it doesn't have to be dynamically updated as often as in previous header compression mechanisms, which reduces complexity significantly, but still gives quite a reasonable compression rate. So the 40-byte IPv6 header usually becomes something like 5 to 7 bytes. And the third one was the architecture. In RFC 6775, we rethought IPv6 a bit. First of all, we embraced a new architecture that was being generated in another place of the Ietf, the multi-link subnet. So we allowed different radio domains to be put together into a single network. And we got rid of the need for subnet-wide multicast. So there's only radio layer multicast and no multicast that needs to reach all the ends of the network. And that's, of course, important if you have sleeping nodes. You don't want to wake everybody just to solve a particular address assignment problem. So the IPv6 neighbor discovery protocol had to be adapted to that. And the basic idea was to actually use a special router in the 6LoWPAN network, the 6LoWPAN border router or edge router, and let this router do some of the work. And that's actually an instance of a general idea that we will find in other protocols as well. We just want to make good use of less constrained nodes. So the edge router, for instance, runs the duplicate address detection and keeps a list of nodes, and it's the only node that really needs to scale with the network. And the reason we can do that is that the Borderite already needs more power to be able to talk to the non-6LoWPAN side. So this is not an arbitrary decision, but it really makes sense architecturally. And yeah, what we also had to do is fix the addressing model. We had to find ways to get by with much less multicast, but I'm not going to go into the details here. So 6LoWPAN was essentially completed in 2012 when we had the encapsulation standard 4944, the compression standard 6282, and the neighbor discovery standard 6775. And since then, we have had updates for the compression and for the neighbor discovery. So we were done at some point and decided we didn't really need the 6LoWPAN working group anymore, but it turned out we needed a working group to do 6LoWPAN technologies for other radios, and that became the 6Low working group. And the 6Low working group really has this smorgasbord of different technologies. Well, some of them haven't happened, like this Hello technology. But there are lots of technologies. There's the radio of the week, as we used to say, that really requires some adaptation work to make it work in the internet. So this is the orange-brown part of the slide. And of course, the important part is that this is not the entire internet, but of course, the IoT also works on power line communication, on Ethernet with power over Ethernet, on Wi-Fi, on LTE. So this is the part that we get just by using IP. And the orange-brown part is the part that we actually have to provide 6Low technologies for. There are a few other network layer technologies that require more work. There is LPWAN, which is essentially millibit networks. So networks that have a sustained data rate that is not a bit per second, but less than a bit per second, measured in millibits per second. And so networks like LoRa or Sigfox actually can make use of IP as well, but they need special header compression technology, static context header compression, which was done by the LPWAN working group. There is also another working group. Oh, this still has the old name here. I'm sorry. There's another working group called DetNet, which looks at running IP networks with the objective to get low latency communication, deterministic networking. And there is a wireless offshoot that Pascal will certainly talk about at some point. Finally, I probably should mention Sixtish, which was an interesting group. Well, it's still active, but it has done most of its work, that looked at a specific system, 802.15.4 in time-scheduled channel hopping mode, and provided the adaptation layer work, so the 6LoWPAN style work based on 6LoWPAN, but also other elements, for instance, schedule management, network onboarding, key management, and so on. So that's why we had 5 plus working groups in this network layer space. Another area is routing, and I will run through this very quickly, unfortunately, because it's actually a very interesting aspect, and I expect there will be a lot more work on routing in the future, but right now there is a role working group. This has done the Ripple protocol and also a MIPL protocol, semi-reliable multicast flooding. And the Ripple protocol is interesting because it essentially builds a tree, or not really a tree with multiple parents, which is a directed acyclic graph, actually. And the redundancies in the tree help cope with churn. So you don't have to update all routing tables when somebody closes a door and propagation becomes difficult. you can just use your alternate parent. So this is interesting work. It comes in two modes. The non-storing mode is probably the more interesting one. And the breakthroughs here were the trickle mechanism for reducing the amount of routing protocol traffic, and the directed acyclic graph, the destination-oriented directed acyclic graphs that Ripple uses to do routing. And that's actually interesting enough that it's actually used in other places now, for instance, in Anima. So again, here we have this idea of making good use of less constrained nodes. The LLN border router is the root of the directed acyclic graph, and we can move some of the work there, so only that node actually needs to scale. Okay, I want to move up a little bit to application layer protocols because we cannot necessarily do all the work with the existing application layer protocols. Of course, we have HTTP, and HTTP is Swiss Army knife, but you don't necessarily want to do all your work with a Swiss Army knife. So two major working groups were set up in the application space. I have to avoid the word area because ACE is actually in the security area. So the core protocol replaces HTTP by a less expensive equivalent for certain applications. And the ACE working group defines security that is less dependent on humans and on very fast upgrade cycles, and embraces the multi-stakeholder Internet of Things. Note that we also need data formats at the application layer and at the security layer. And you may have noticed that the industry has been moving to JSON for data interchange. We used to use XML a lot. We're using that less. We're still using it, but we're using it less. And many things are done in JSON in the big internet. And CBOR is kind of the little internet equivalent to that, where JSON is too expensive. You can use CBOR. And we also have security formats, JOSE for JSON, COSI for CBOR, we can use in this space. And finally, we have work on semantic interoperability for the actual application data, which, if I have time left, I will talk about at the end. So CBOR is an activity that started in 2013, not as a working group. The working group has only been created in 2017. But this is essentially a binary, a concise binary object representation that starts out from the JSON data model, but adds binary data and an extensibility mechanism. And that's used in a lot of IoT activities now. Another interesting development is that of CDDL, which is essentially a description language for CBOR. Just as you would be using ABNF to describe your text-based protocols, you can use CDDL to describe your binary protocols. So if you know what XC was to XML, well, obviously CBOR is the binary form of JSON. And we actually looked at a lot of binary JSONs before we decided to define our own, but these were all more or less hopeless on the constraint side, so we didn't use them. So that was preliminary, and the interesting working group that was created here and that is still very active is the core working group in 2010, Constrained RESTful Environments. So in 2010, we are pretty much well understanding what we wanted to do in 6LoWPAN, but we looked for a 6LoWPAN application protocol, and that is what turned into core. We decided that the most interesting architecture for an application protocol here would be the REST environment. And that's just the idea that the web has been incredibly successful. To use this in the Internet of Things, we need a replacement of HTML, and I've talked about CBOR as a building block for that, but we of course need more. We can use URIs in the same way we're using them in the big web, but it probably makes sense to have an alternative for HTTP. So we have a less resource-consuming protocol. HTTP comes with a lot of historical baggage. And so we decided we wanted to keep the representational state transfer model of HTTP, but not try to somehow compress HTTP for constrained node networks, because compressing means you save bytes, but you still retain all the complexity. So we decided to do something that is simple. And that simple thing turned out to be CoAP, the Constraint Application Protocol, which implements HTTP's REST model, but based on a very simple protocol that initially started out as datagram only, with a 4-byte header and a compact but simple options encoding, and various additions to the architecture, like the observe mechanism that lets you stay informed about the status of IoT components. So this almost looks like HTTP, but the underlying mechanism is much simpler, with a protocol that really uses bits and bytes for doing things, and that doesn't require parsing text. CoAP and HTTP are compatible enough that you just can combine them. So you can define proxies that sit between the HTTP and the CoAP world, so that there is no need to do very, very harsh separation between CoAP and HTTP, but where you want to use HTTP, you just use a proxy. And the standard caching mechanism from HTTP also applies here, so you can save a lot of exchanges by simply using caching. The new element is observation, which means when you ask a server for a state, so for instance, you could ask a server for the state of the light resource, you can get a reply with the current light resource, but also if the light resource changes, the server sends you additional responses with the changed state. All this is done in a very, very simple way, very little complexity. So it's actually very useful to stay informed about, for instance, a temperature sensor or a light switch. And on the other end of the complexity, we have block transfer. Since this is UDP based and we want to keep our packets small, it's sometimes necessary to split up a single interaction. So you cannot do a software update in a single UDP packet. So you use something called block transfer. So the breakthroughs that Kaur gave us was we have REST. We get rid of the HTTP baggage, and we extend REST with the observe model, which is really important in the Internet of Things. But we also added something based on web linking for discovery. So finding out information about a thing that you find in the network. And there is a resource directory on top of that that is about to be published at this point in time. And Core actually didn't stop at that. So there are a lot of additional documents. And if you have the slides, you may want to look this up. There is also a need to go beyond the self-description capabilities that Core provided, something called Semantic Interoperability. And I don't have time to go into the details, but since Mars probes actually crashed because it wasn't documented whether something was a metric or an imperial measurement, that's something that doesn't happen to NASA people only. It happens to IoT people a lot, and we really are better off if we have a way to keep descriptions about the IoT devices that we are using. And out of Zigbee, an activity called One Data Model was created that is trying to collect models and shape them for common use and reusability of common devices. They have some 200 models right now of refrigerators and temperature sensors and fans and heating elements and so on. But to do this, you need a common language to describe this information in, and that's the semantic definition format, which is now running in its own working group, the ASDF working group. And the idea is not to just create another competing standard, but to design something that really helps in translating from the ecosystem specific data models. Every organization, every SDO in the space has their own data model mechanism. And the point about SDF is that you can translate from these ecosystems models to SDF and back or to another ecosystems model. And the RFC from that is nearing completion. Let me quickly run through security. Security is not optional. Definitely not in the IoT. And we started out with some pretty heavy security when Kaur was designed. So by 2013, 128-bit security was not the norm in the big web. And we just started out by saying we want to have it in the little web because our devices are unsupervised and just need to be as secure as possible. So for a long time, we just said CoAP comes with DTLS, the datagram version of the Transport Layer Security or SSL protocol, and that provides our security solutions. But then at some point, we looked at the whole stack and looked at other places where we might be able to provide security. So transport layer security is above the transport layer. We could be using IP security. That was actually on the cards when we started CoAP, but we found out this was hard to deploy. But we also can run security at the application layer. And RFC 8613 tells you how to do object security for constrained RESTful environments. And that's a completed standard, but we are currently working on providing infrastructure for that. This standard could be done quickly because before that, we had already started defining object security standards for the IoT. So you know about CMS, which is the basis of SMIME, and XML-DSIG, which is the basis of SOAP, and HOSI, which is used in the web. And we define something called COSI for the Internet of Things. And this is essentially using CBOR instead of JSON, repairing a few things that we have learned about HOSI and was published 5 years ago in 8152. And the one thing that is currently being worked on is in the Lake Working Group is a protocol for setting up the keys that will be used with OSCORE. There is an ephemeral Diffie-Hellman over COSI document, and that defines a lightweight authenticated key exchange. So this is a lot of security infrastructure, but then IoT devices really are applications, and you need to think about security at the application level. So we are pretty good in protecting objectives in the right way. So we know how to do 128-bit security and all that, but we are not necessarily always very good in protecting the right objectives. So we don't necessarily fully understand what we need to achieve. And yeah, the sorry state of IoT security in the so-called real world, where we often only have perimeter protection and the Wi-Fi password is the keys to the kingdom. But we need authorization. And for that, we created a working group called ACE, Authentication and Authorization for Constrained Environments. And as a first step, this working group started using the popular OAuth framework from the web. and making that available in the constraint space. So yeah, this is what we want to enable, a constraint client talking to a constraint server. And in reality, we have to think about all these, yeah, I cannot say things or components because there are people on here. So the constraint devices probably have some less constraint devices that help them doing their job. And these less constrained devices in turn are controlled by people or organizations. So we really have to model that whole thing to get a reasonable application layer security. And there's actually a theory behind that I don't have time to explain. But it really is about certain fundamental principles that need to be maintained, and from which certain fundamental tasks are springing that need to be done in order to actually be secure. But the most important observation is that authentication always requires authorization. Well, you think I would be saying the inverse, authorization requires authentication. Yes, of course, but authentication is not binary. So it requires authorization again. That's something that needs to be considered. But in the end, it's again an example of making good use of less constrained nodes. So the simple devices can run business logic independent protocols and can delegate business logic decisions to less constrained devices. That's where we need to get to. We also have to look at the life cycle of devices. Devices aren't static. They are manufactured, they're being installed, they may be commissioned, and maybe at some point you have a software update and then you reconfigure your application, you decommission your device, remove and replace it, and maybe even reuse the device for a completely different application. And of course, you don't want remnants of your old security settings in your new application. So there is an IETF document about that is guiding further development in this space. Let me quickly talk about IoT devices as an attack platform at the end. So you don't just want your devices to be secure so they can do their application. You also don't want IoT devices to be usable as an attack platform. And unfortunately, IoT devices have been used as an attack platform a lot. And the question really is, who is responsible for making sure that IoT devices are not an attack platform? And of course, you could say, well, it's the owner of the device, of course. If you create something that creates a hazard, then you have to control that hazard. But obviously, most users of IoT devices cannot do that. And they also are not so likely to employ a garage like you would employ for the brakes of your car. You do that because there is actually regulation that makes you do that. The other approach, of course, is to say, well, the vendors have to make sure their devices are not dangerous. And we have things like CE signs or UL signs in the US. We have regulation and so on. Yeah, that's not all in place at this point in time. So what we're actually building right now is jails. So we put these IoT devices into environments from which they cannot escape. We are protecting the network from the IoT devices, which is a bit weird, but makes sense if you consider them dangerous. And one standard that has been created to facilitate that is the manufacturer's usage description, or MUD, defined in RFC 8520, which provides an authoritative statement about a device, what that device should be allowed as its communication behavior. So the network can take the MUD description and essentially jail in the device except for the behavior that it's supposed to provide. Another functionality that is required to make IoT devices secure is to allow for software updates. If you cannot update your IoT device, then at some point you will have to discard it. Bugs are being found, environments change, and so you have to respond with a software update or with throwing away the device. And traditionally, we did this using special updater devices. So you connected your IoT device to a PC and ran a special application on that PC. That's way too expensive when we go into orders of magnitude of devices per people. So we need secure over-the-air upgrade. And there's actually a working group for that, the SUIT working group, that is defining a manifest for a software update that can be checked by the device, so the device can protect itself as far as possible to make sure that only legitimate software updates are installed. And the work of the SUIT working group is nearing completion now. And it's, of course, based on CBOR and COSI, and it's described in CDDL. So you see some of these base standards being used there. The final working group I want to talk about is the REDS working group, which really is picking up the observation that securing the communication is not enough. We need to secure the end hosts. And because we know we will be limited in our ability to do so, we need to be able to find out about the security status of an end host. And that is done using attestation procedures, or in this case, remote attestation procedures, because you're trying to find out something about the device that you only have a network link for. So you need that device to convey some evidence to you about its status, and you need to support systems that appraise this evidence. The REDS working group is completing its architecture right now and has a few initial drafts for protocols. So I really did a little bit of short shift to security here, but I really want to show this last slide here, which is, if it's not usably secure, it's not the Internet of Things. I mean, it might be something, and it might be connected to the internet. It might contain things, but we really cannot afford to build an Internet of Things that is not usably secure. So we do need those activities. Thank you.
Thank you so much, Carsten. Let me just quickly see if we have any questions. I don't see anything in the chat or in the Q&A. If anyone has any questions, now is the time. Okay. Seeing no questions, and in the interest of time, maybe let's just move on.
Praneet, if we have time,
there is a
question,
panelist. Yeah, but I see a hand. It's up.
Hey, Carsten. Yeah, it's me. Am I audible?
We have Rahul raising hand. Rahul, could you speak for yourself?
Yes. Hey, Praneet, can you hear me?
Yes, yes.
Okay. So, Carsten, a quick question. Thank you for the talk. Great. I've heard you time and again, and every time I hear you, there's always something new to learn. Thank you for this talk. So, Carsten, one thing that stands out from this slide is that there is absolutely zero mention of IPv4 technologies in this. And at some point of time, we have IoT Directorate has taken a decision not to include IPv4. So I'm just keen to understand what is the background. So if you can shed some light on that. Thank you.
Yeah, actually, if you look closely, you could have found a few places where IPv4 was mentioned, but not under that name. So for instance, we ported CoAP from UDP to TLS in order to be able to do net traversal. So we are, of course, aware that there is an IPv4 world out there. But typically, protocols are being developed for IPv6 first. And yeah, you can, of course, make all of the application protocols work in the IPv4 space without really very much change, just the format of the addresses change. But the network layer work really has been focusing on IPv6. I agree with that.
But are you saying that, so if I may have a quick follow-up, are you saying that it is still okay to bring in IPv4 proposals to these working groups? If there is, because I saw a circular saying that it's better to just support IPv6 at this point. There's no point in supporting IPv4. I've heard that in more than one context. Is that a true statement?
It's definitely a complex issue, and of course you cannot ignore the reality that a lot of industrial networks are IPv4 based. But on the other hand, where we actually define new network structure, I think it's okay to think about IPv6 first.
Okay, thank you. Thank you.
Thanks.
And Michael, of course, has a nice saying in the chat. If your IPv4 proposal is so that you can continue to ignore IPv6, then probably you will not be welcome. So that's an interesting perspective on this.
Carsten, we have a few more questions. Q&A is flooding with questions. If you don't mind, could you open this window and see? And also, meanwhile, I'll raise the question for you. The first question is from William, and he says, it would seem that an IoT is only as secure as the least secure piece of hardware. After that, he writes, from who knows what a source, is that true?
Yeah, that's actually, there are two parts to this question. First of all, of course, you have to define your system so you can do some isolation. And MUD, for instance, is designed to support isolation of systems that are misbehaving. So why did the question just go away? The other observation, what source? Actually, we have had a long discussion about data authenticity. So we know something about sources, but in a more general way, there is a new activity going on right now called SCIT that really wants to look at supply chain information in more detail. So there is a software bill of materials activity that essentially started with an executive order by the US president. And that has woken up a lot of people to the fact that they don't really know what software is in their systems. And the software bill of materials activity, or generally the supply chain information activity, will make this more transparent over time. So at some time, you may be in a position to actually get a CVE, the vulnerability report in, and know exactly and immediately which components in your network are actually affected by that CVE. That's where we want to go to. And certainly also for the IoT. What procedure should follow by a person to make his protocol as an Ietf standard internet draft? Now that's a long question, and Fred Baker has some nice slides about that I'm not going to try to repeat in a minute-long response. But one good way to do this is actually to contact someone who knows how to do that and go through what needs to be done. So Vishal, if you want to contact me, send me some mail, what your idea is and what you think should be standardized. I can certainly help you make that happen.
Thanks, Carsten. And now I see a hand raised by Michael. So Michael, do you want to unmute yourself and talk?
Certainly, thank you. Carsten, you covered a whole lot of material extremely well. Probably some kind of a record. I had two questions. One is sort of on the other side of Drew's question, which is, if we project forward 5, 10 or more years with all these huge numbers of devices, is IPv6 enough, or will we have to do something beyond IPv6. And my other question, I'm going to kind of package them together here. You mentioned about using unreliable protocols, and to me that means maybe more UDP than TCP. First off, did I interpret that right? And if so, does that present any challenges in and of itself? Again, thank you for everything.
Yeah, let me address your question about IPv6. Well, IPv6 addresses are large enough to do a lot of things. And what we are discussing in various places right now is whether we actually need to make some progress on the kinds of things that actually are addressed by IPv6 addresses. So that there is this semantic addressing or semantic routing work going on right now. And I'm pretty sure we will have some interesting ways of, for instance, addressing services instead of hosts 10 years from now. What was the other question?
The other question had to do with the use. Are you projecting the use of more unreliable protocols, i.e., more UDP, less TCP, and does that present any challenges?
Well, the problem really with the IoT is that there are things in there, and these things are unreliable in many interesting ways. The fact that the network may not always deliver all your packets is just one of the unreliabilities that you have to work with. And UDP, of course, doesn't make sure that your packets arrive, but then we have application protocols like Kaur that do that for you. So, of course, you shouldn't be using UDP in a fire and forget way, but you should make sure that the way you're using these transport protocols is appropriate to the problem you're trying to solve. But just as another piece of information, the QUIC protocol, which for many people is replacing TCP in a number of applications, is now getting unreliable components, unreliable programming interface as well. So sometimes this unreliable approach is actually exactly what you want.
Makes sense. Excellent answers and great presentation. Thank you again.
Thank you.
Thanks, Mike, for your question. And now, Carsten, we still have 2 more questions in the Q&A window. But before I proceed with that, we are running short on time, so maybe we could take them briefly. First one is by William, saying wireless was mentioned in your presentation. Given the rapid adoption of the 5G wireless standard, can you comment on the Ietf IoT work and the adoption of 5G as the probable wireless solution for IoT?
Well, yes, of course, 5G has interesting ways to connect things, but there are other interesting ways, and I may not want to use 5G within my home or within my building network for one reason or another, or I may. So that's just one of the choices you get with IP, and that's what makes IP so powerful, that you actually do get this choice of technology providers, but choice of technologies in the first place. So yes, so there is something, for instance, called NB-IoT, which is an interesting protocol to do IoT on.
Thanks, Carsten. And now finally, I think we can take one last question by Glenn. Glenn is asking specifically if someone wants to get, someone who is new to Ietf wants to get involved with the IoT work happening at Ietf, are there any recommended readings that you can suggest?
I wish I had an answer for that. So 10 years ago, when 6LoWPAN was completed, I actually wrote a book about that. And maybe it's time to do another book about IoT. But the field is so complex now that I actually think events like the current one are exactly the best place to get into contact. And of course, there are lots of IoT events out there, and it may be a little bit hard to find the right ones, but I think you are in the right one.
That's right. Thank you so much, Carsten. Since we are a little bit over time, I'll just hurry to the next session now. But before I do that, I would really like to thank you again for the illuminating talk. It is always a pleasure to hear you speak, and this time was no different. And you have indeed set a great landscape and a very smooth cakewalk for us if we want to get engaged with the Ietf, with the IoT working groups or the work areas, or whatever development with respect to IoT is happening at the Ietf, because that itself is a challenge. Ietf is so diverse. Finding the right working group, finding the right work and right people is always a challenge. So thanks for that. And as always, it is a pleasure to have you at Connections. Now, without wasting much time, let me just move on to the next session for today, which is the IoT webinar series Kickoff. As some of you might already know, we have been conducting these webinar series for over a year now. And in the past, there was the IPv6 webinar series, which we did in 2 phases, phase 1 and phase 2. The phase 2 actually just got over in March. And now this month, April, with this event, we are kicking off the IoT webinar series. And we have with us our own Pascal, Dr. Pascal and Georgios to help us out there. I'll just start with our introductions, very brief introductions, because again, Pascal and Georgios are such accomplished people that I don't have enough words to fulfill and do justice to the intro. Dr. Pascal is an expert in IPv6 routing and meshing technologies for the reliable wireless mobility and data centers. And he has been actively involved in research and development of standard efforts on internet mobility and wireless technology since the year 2000. Dr. Pascal currently works at Cisco's Chief Technology Office, and he has co-authored for over 20 RFCs at the Ietf, out of which 2 are actually routing protocols, the RPL, which is one of my favorites again, and the RIP routing protocol. And most of his work involves with IoT, deterministic networking, and IPv6 neighbor discovery specs. He has also contributed to several other organizations such as ISA, IEC, and ETSI. Before we start, I would like to quickly introduce Georgios as well. Since the introductions are quite lengthy, we've split it into 2 slides. Dr. Georgios serves as Associate Professor at the IMT Atlantic in France. And he has more than 60 peer-reviewed publications and is indeed quite a name in the academic community at an international level. He's actively involved in the Ietf standards development, and he currently has multiple ongoing drafts in the role and raw working groups. If you're interested, please feel free and to browse. His research interests include industrial IoT, 6-dish, 6LO, LoRaWAN, and LPWAN in general. Now, without holding a lot of your time, let me just hand off the floor to you, Dr. Pascal and Thubert. Thanks for being here with us, and off to you.
So thank you very much. And I'm trying to share the slides from the screen that I would like to be looking at when I speak to you guys, but apparently PowerPoint 3 wants the screen up there to be the slides, which means they'll be looking up there, which means they won't be looking at you, and that's sad. But okay, let's start with this because we can't waste too much time. So let me share my presentation, and please confirm that you're seeing it okay.
Yes, Pascal.
Okay, neat. Okay, so basically, what's going to happen is we're going to give a suite of webinars, like 5 webinars, and a number of the presenters that you saw today. And this will happen in the course of May and June. And there will be 2 aspects to this webinar. One aspect will be 1 hour effectively webinars that we will do online. And there will be a counterpart to that, which is a MOOC that is being recorded and that Georgios will present after my talk. And this MOOC is something that people will be able to follow offline, asynchronous to the webinars, but the MOOCs will develop further on the things that we will be discussing during the webinar. So it's kind of something that will probably work, hopefully will work well together. So I will be introducing the series of webinar, and then I will give the ball to Georgios, who will be presenting the MOOC itself. So quite interestingly, introducing the same topic as Carsten, I'm actually inclined to take a slightly different angle, and that's very interesting because we actually worked a lot together in the course of the last 20 years. But yeah, there is so much to be said and so much angles to everything that hopefully I still have something to say. So first thing that really strikes me when we talk about IoT is there is something that happened 20 years ago, pretty much 25 years ago, which changed everything. And we are so used to it that we don't necessarily realize. But 25 years ago, I had a single PC at my home, and that PC was connected with a modem. And that was the only computing thing I could have at home. The real limit was not how complex computing was. The real limit was how complex connectivity was. The only way to connect was pretty much this modem. I could do 56 kbps at most. And clearly, there was nothing like a radio. And in the course of computing, a new thing came in, which really changed everything, just like the 5 fingers changed the evolution of life on Earth. The wireless changed the evolution of computing and the usage of computers in incredible fashion. The key thing, I guess, that wireless brought to the picture is the fact that you could connect many devices, not just one, and that connecting each additional devices was very cheap. Once you pay for the AP, basically, or something similar, you can connect many devices. So the cost of connection becoming very, very small, it becomes possible to connect a great many devices, but then you think, hey, those devices don't have to be huge computers anymore. Since everything is cheap, you can also think about connecting cheap devices. And that's when we moved from basically, big computers and personal computers to a model where you could connect your phone, you could connect any device. And so really what allowed what we'll be talking about today, and mostly the IoT Internet of Things, but also the phone as you're using it, is the arrival of those radios technologies. And by radio, I don't mean necessarily just Wi-Fi and 4G, 5G, and we'll be going through a number of radios that are not those ones. But basically, I'm talking about radios with range of meters to kilometers. And those radios allowing to connect a great variety of devices is really what enables the next phase of computing, which is phones, IoT, all those devices which are really computers, but don't look at all like your own PC. And so yes, not only could you connect many devices, but the deployment in places where network was not, for instance, an existing factory, an old factory, a century-old factory, was deploying wires there was pretty much impossible because you could not even pass the wires. And with wireless, all of a sudden you could connect network a lot of places where wires were just impractical, or if they could be done, that would be very, very slow and very, very costly. And then yet another aspect for the utilization that wireless enables is the distance, right? Some satellites cover the whole Earth, but even if you think about short distance radios, we can build mesh networks which cover whole areas, and that's what we do for the smart grid. You can have networks which can literally cover a few centimeters, like NFC. You have every distance in the middle. And so wireless really allows you to connect all sorts of devices over all sorts of distances for a very low cost. And that's really, in my mind, the key enabler for everything we're talking about here. So we forget, but it's kind of, yes, I mean, at the beginning of times, there was this. So probably the place where most of the, not all, but most of the standards that we think about are being developed is the IEEE. So there is a big exception, obviously, with everything 3G, 4G, 5G, which is developed at HC by the 3GPP. But apart from that, most of the networks you're thinking about are effectively developed at the IEEE. And the IEEE is a complex structure which does not really operate the same way as the Ietf does. So I'll be coming back later on the way the Ietf works. But here, what you're going to have is a number of groups working on all things electric. And one of those groups is actually called 802. 802 is working, is producing networking standards. And 802.3, for instance, is Ethernet. 802.5 was token ring. So you see networks which are from the wired world. 802.1 is bridging. Now, for wireless, a number of groups have been formed. One of them that you know very well is .11, which does Wi-Fi, wireless LAN. But there is also 802.15, from which a number of a real family of radios have come out. And most notably, you all know Bluetooth. Well, Bluetooth is 802.15.1. A number of you, you've heard about 6LoWPAN. The LoWPAN in 6LoWPAN is really 802.15.4. 802.15.4 was a radio that was defined with effectively the IoT in mind. So the idea was to be low rate and to be low power. So it's a very simple MAC, and you can easily place your application over it. That was often confused with ZigBee, but ZigBee is really a stack that is missing a network layer, actually, which really builds the application right over 802.15.4. So ZigBee is the stack without a network layer. And 15.4 is the radio that sustains ZigBee. Now, since the early versions of 15.4, a large number of variations of 15.4 have come out. Some of them, most of them in the 2.4 gig band where the initial Wi-Fi was as well. So that's the ISM band where the 802.11b happens, for instance, happened, and then a great many of the followers. And then clearly there is also the 5 gig, etc. More interestingly, 802.15.4g developed radios in the sub-gig band. So that means 900 megahertz, for instance, in the US, and 868 in Europe, something like that. There is a lot more bandwidth actually in the US that's free for the sub-gig band than there is in Europe or India or Japan. In India, it's really, really narrow. So, so that's 802.15.4. And one thing I need to add on this is part of the ways that differ in the Ietf and the IEEE is for a spec to be alive at the IEEE, for instance, 802.15.4, you need to periodically republish it, like less than every 10 years, something like that. So what happens is between two of those publications, a number of task groups, like 802.15.4e, which produced what we call time-slotted channel hopping, and we'll come back on that. They define a temporary standard that we call an amendment. And at the end of the less than 10-year period, the amendment is retrofitted into the main spec. For instance, 15.4e was published as an amendment in 2012 and was retrofitted in the main 802.15.4 in 2015. And then there are other standards. The one I really like is 15.6, which is a body area network, which has 3 variations in it. And one of them is actually a polling mechanism for those who knew old wires. It's a bit like HDLC or SDLC. So it's a central point polling every devices and asking them if they have something to send. And this makes a very, very efficient network for body area. So really the idea is to cover the zone of your body, and that would be it. So a lot of work happening at the IEEE. And most notably for our concern, which is IoT and operational technology, by which I mean factories, automation, car automation, everything automation and stuff like that. 802.11 is working at porting on radio the concepts that have been developed in 802.1 for deterministic networking. So in 802.1, there is this group called TSN for time-sensitive networking. And a lot of work is happening right now in the context of 802. Wi-Fi 7, basically, to bring in some of the capabilities that you find in 802.1 TSN. Okay, so yes, so now we know the IoT basically mostly needs radios. There are IoT use cases which operate on wires, some of them even on power line. But as we saw, for ease of deployment, for scalability, for many, many devices, chip deployment, most of the IoT use cases are based on radios. And with this come a number of constraints. For instance, spectrum is not infinite, and spectrum is shared for the most piece, unless you think about 4G, 5G, which have dedicated spectrum. But even if it's dedicated to your usage, there is still a limited amount of spectrum to be shared between users. And you know that when you want to use your 4G telephone, and sometimes you have a huge throughput because you're alone, on an antenna somewhere with low density near the antenna. And when you move to another place in a city, crowded area, all of a sudden your throughput goes down. That's because the spectrum has to be shared. Now, regardless of which spectrum you're using, and for the most piece, regardless of whether it's dedicated spectrum or not, there are tons of things which can interfere, including yourself, actually, like echo of your own transmissions, which we call multipath fading. And then obstacles in what we call the Fresnel zone, which is basically the kind of an oval zone between the transmitter and the receiver. A lot of things can hinder the transmission. So compared to wires, there are a lot of challenges, a lot of constraints that an IoT or an OT application has to go through with wireless. And then there is another set of constraints which comes from applications. In particular, again, in automation, if you have a control loop, you want a very deterministic delivery of your packet. And by deterministic, I mean very reliable, always on, because your car is driving. You can't just stop sending the packets, and what will the car do? And a critical one to keep the control loops in phase is latency. Otherwise, the control loop can really go crazy. So ensuring latency means that you can't retry forever. You have to find a way, and in particular in wireless, that can be difficult. You have to find a way to deliver your packet. And the key, actually, in the case of wireless, the key to deliver your packets is what we call diversity, being diverse in usage of spectrum, in usage of technology, in usage of paths. So spatial diversity, coding diversity, the way you encode on the radio, et cetera, et cetera. And then, as Carsten alluded to, there are all the constraints which are coming from the device itself. If the device is battery operated, then you've got limited power. Transmission requires power. So you have to limit your transmission. How much energy will you dedicate to routing, for instance, in a mesh versus to sending packets? How much memory do you need for operating your protocol, et cetera, et cetera. So many forms of constraint that we have to live with. Now, when I was young, the mail was a dedicated network, very slow. You had to write a letter, put it in a plane or a ship. And if the ship doesn't sink, then eventually your letter would go through. Telephone, when I was younger, I was moving in the US or what, I had to pay huge amounts of money just to call my wife every other day. And then TV, I needed a different TV and different everything if I was in the US versus I was in France. And all those operating all those networks was a lot of operating OpEx, actually, because different wires, different technologies, different devices, different people operating them. OpEx, CapEx, I mean, that was a lot of spending just to maintain all those networks. And what really changed everything is the arrival of the internet. And all those technologies, as Carsten again alluded to with email, they all, with voice actually, they all converge onto the internet. And for each of them, you find that price has gone mostly to zero, but more interestingly, new capabilities were found on the way. For instance, for me, email is a lot more interesting than before, not just because it's free or because I can send high volumes of it, but because I can archive and dig years of archive in minutes. And then, as you know, Skype and WebEx, compare that with the plain old telephone system in terms of quality and just video and just conferencing as we do now, etc., etc., etc. But IoT and operational technology have been a lot slower to migrate to IP, and you might wonder why. And for a large piece, it was because IP would not provide the kind of services that IoT and operational technology, OT, would effectively need. Now, the first question, and that's the one that Rahul asked earlier, is which version of IP would you be using if you wanted to port IoT and OT over IP? And as you know, we are kind of running out. We've officially run out of IPv4 addresses. And on the other hand, if we evaluate the number of devices that IoT represents, I mean, it's tens of billions. So in the one hand, you get a source of addresses, which is mostly empty. And on the other hand, you've got requirements for addressing devices, which is in the order of billions and ever growing. The trend that we are now seeing, and that's the picture on the top left, is that IPv4 addresses, because they are depleted, they are now becoming a resource that you can buy and sell. And the price is going up. And it's very fast, actually. It's around $60 these days. And it's going high and high, and we don't even know. We have estimations, but we don't even know how fast the price is going to climb. And for an IoT device, which is very, very cheap, I mean, can you pay for a very expensive address, which will be actually 10 times more costly than the device that it should address? And one last thing, but quite interesting, is that, yes, a lot of the devices and the IoT research is being done in the US. In the US, you have pretty much five IPv4 addresses per head count, per person. But if you move to Europe, for instance, that the picture on the bottom right, Europe is kind of orange on this picture to brown, and that means less than one IP address per person. And then if you go east or if you go to Africa, then it's going to be 10 person per IP address, something like that. So you don't have a single IP address per person outside of the US, pretty much. How could you use IPv4 to address your devices? So at some point, one big reason why we decided we went for IPv6 from day one is because we saw those curves, and you know, they have been there for a while, and we knew that there was no way to address the devices and do it in a cheap fashion if we did not just go for IPv6. And then there was the other point that Rahul and Michael and Carsten discussed, is that effectively the Ietf is very much IPv6 oriented, and pretty much every development that we make, you know, for use in the future, and we see that the future will require IPv6. That's how we see it. So we kind of develop everything for IPv6, and if you need to backport to IPv4, it's usually quite easy because you can, for instance, embed IPv4 addresses in your IPv6 address. That's how we did 6PE, for instance. And so it's always doable. So basically, yes, all those protocols that, you know, Carsten has enumerated, they have been developed in the context of IPv6. And then comes the Ietf. So Carsten already spoke about a lot of that, so I won't insist again. Just to let you know that I selected just a subset. Oops, sorry, don't want to move that slide. We selected a subset of them, and these are the ones that developed the technologies that we'll be discussing in more details during the webinars, and that are also present in the MOOC. So 6-ish is the one where we ported all the technologies that you see here together. Really, the 6-ish group is interesting for that. Is we ported everything together and created an architecture, a proof of concept that really packages all the standards that the Ietf has been doing or was doing at the time, to make sure that they could actually work together. And not only did we standardize the architecture that brings everything together, But also we did the open source implementation and all the interop tests between multiple implementations to ensure that effectively you could build a 6-dish stack. So when we talk about a 6-dish stack, yes, it's over TSCH, but most of what it really means is bringing all the rest that you can see in this list together over that particular MAC layer, which is a variation of 8.15.4, as I said earlier. So yeah, the charter was, on the one hand, deterministic, and by deterministic, like I said, we mean reliable, available, and capable of bounded latency delivery. And for that, effectively, the TSCH MAC is a large improvement over the classical 15.4, in that you can dedicate time slots and navigate through the frequencies. So you can effectively optimize the diversity of the transmission. If you include ripple for diverse path, then you kind of optimize the diversity that is available. And with that, you increase the reliability and the determinism of the MAC layer. So as soon as you've got a deterministic MAC layer, the question is, can you do deterministic and stochastic IP over it? And that's what DetNet looks at, and that's what Rahul looks at now at the Ietf. The most important piece, and that will be the first session of the webinar, is that the 6-dish architecture brings them all together. It shows where the different RFCs could, for instance, overlap, in which case we say, oh, it's going to be done this way. Or if there was a missing piece, then we effectively went to the working groups and say, hey, you know, in your standard, you missed that piece because otherwise you can't plug this other standard over it. And that's how, for instance, we pushed for RFC 1910, which is how you can register an address from a host, a 6LN in 6LoWPAN terms, from a host to a router, the first hop router, and how that registration, which is done with 6LoWPAN ND, can be injected into REPL. So now we have combined the host to router interface, which is 6LoWPAN ND, with the router to router interface, which is REPL. So all this kind of activity happened because 6-dish actually tried to build it, did the interop test, and figured out what was missing and what needed to be specified. And 6-dish ended up with the stack that you can see here. So a lot of components that Carsten already alluded to. Part of the missing things which were not to be defined in another working group were defined in this group. And this includes what you see called SF on the right, which is the scheduling function. So that's basically how you will tell on which time slot, which frequency, a certain IP packet will be placed for forwarding to the next hop. And then this 6-stop sublayer that you can see here above TSCH, which is what we classically call an adaptation layer, which allows to basically push a packet and indicate effectively what kind of treatment you expect from the lower layer. And then all the components that you can see here, 6LoWPAN ND, REPL, CoAP, 6LoWPAN data compression, and neighbor discovery, and 6LoRH, which is one of the RFCs that Carsten alluded to as well, which is the extension to HC for REPL, 6LoRH. All those will be the topics that we'll be discussing during the webinar. The webinar will be presented by the people that you see today for the most piece. So Carsten will be doing the first session. Then I'll be doing one on TSCH. Georgios will discuss 6LoWPAN. Rahul will present REPL. And I will be discussing about the future and how we progress the 6LoWPAN ND and REPL for the next stages. Which gives us basically this program. So yes, general introduction end of April, Carsten, 6-dish, and the integration with DetNet and RAW for deterministic packets, and which cover a number of RFCs and draft in progress. On May 26th, it's going to be Georgios. June 9, Rahul, and maybe a little bit of me will discuss with Rahul exactly how we do that. And 6LoWPAN and REPL integration future, that's going to be the ending this webinar series on June 23. And that's pretty much my presentation. And with this, I will give the ball to to Georgios. Georgios, I will stop sharing if you want to take over.
Thank you so much, Pascal. Can you confirm that you see my screen?
Yep.
Yes.
Hello, so my name is Georgios Papadopoulos. I'm an associate professor at IMT Atlantic. And I had the chance to work with some of the guys who are presenting here, like Rahul, Pascal. So today I'm going to present the MOOC that we are working on, which has strong correlation with the webinars that Pascal previously presented. So I will show you the details of each week of the MOOC, and at the end, I will show you the correlation that we have between the MOOC and the sessions of the webinars. So we have, like in any typical MOOC, we have 4 weeks plus the welcome week, so the week 0. So we try to have 1 week per layer, per 60 layer, from MAC to the network. I will go in the upcoming slides into a little bit of the details. So we are 4 permanents that from IMT Atlantic that who are working on this project. In addition to our work in terms of the readings, videos, and quiz, we do have interviews from industrial communities. So far we have, Pascal has already given his interview for this MOOC. We have Thomas Vatain from Analog Devices. And we have Remy Duval from Enedis. So it is the French Association for Distributing the Energy in France. So in order to go a little bit into the details, so what we have is the first week, the week 0, the welcome. So basically here will be the introduction in the MOOC, and we will explain all the weeks that we will have in the MOOC. We will explain the requirements, the industrial requirements for Internet of Things, the motivation behind, and we will give an overview of the simulator, or the tool that we are going to use during our lab sessions, which is called Contiki Next Generation Operating System, or Contiki NG. So the potential students will, after reading each week, after going through the videos and doing the quizzes, we'll have some lab sessions, like in typical university lab sessions. So we are working in order to upload the whole simulator online on Coursera. So I forgot to mention that the MOOC will be on Coursera platform. And then within this welcome week, we will give an overview of the potential topologies that we may have, such as star, tree, and mesh. So as a content we have in this welcome week, we have the readings to present all these inputs, the introduction and the motivation, and the videos for the Contiki NG to show the platform, to show the setup, the navigation, to understand the whole simulator. And at the end, we have a video which is related on the topologies in the Iot network. So the first week, as I said before, it is dedicated for the MAC layer. So we will start by giving the background on fundamental MAC approaches. So it means regarding the contention-based and on the contention-free protocols. So the random access, such as the historical Aloha and CSMA, CSMA-CA, CSMA-CD, and so on. And then we will present the contention-free MAC protocols that are based on either TDMA, time division multiple access, and frequency division multiple access. And at the end of this week, we will dedicate a lot of energy on presenting the protocol that Pascal was talking earlier. That's called TSCH, which stands for time-slotted channel hopping. And the idea is why it is so important, this TSCH, what is the novelty of this protocol, and we will have some performance evaluations for the students. So you see here in the bottom, the students will be able to set up a network, to run the network, and to do some reconfigurations in order to see the performance evaluation, for instance, when we are increasing or decreasing the size of the schedule of the TSCH schedule. As well, for this week, we will have the readings. We are working on, well, we have already some of the videos, quizzes, and the exercises. For instance, the students should be able to calculate the collision probabilities when we are talking about contention-based protocols for Aloha and CSMA, and for the network reliability levels. The week 2 is dedicated for the 60s. So we have the 60s adaptation layer, and we will focus on the following RFCs. So basically, we will present the overview of the 60s architecture, RFC 9030, and then we will have these two standards that will present the 6P protocol, which enables the distributed scheduling in 60s networks, which means that how the 6P allows the neighbor nodes to add or delete TSCH shells to one to another. And the last item here is the MSF, minimal scheduling function, which defines the behavior of a node when joining the network and how the communication schedule is managed in a distributed fashion. Again, we have always these 4 items: readings, videos, and quizzes. And finally, we have lab sessions on contiguous operating system. So here we will have 60 space networks now, again, to run, to configure, and to see some performance of the network. The third week, and as we are going up in the 60s protocol stack, we are in the 6LoWPAN now. So the idea here, first, to present some overview of the IPv6 and the motivation behind of 6LoWPAN, why we need the 6LoWPAN adaptation layer. And once we have this background, the idea is to present the series of these 5 standards, RFCs. So basically, we have the header compression, 6282, fragmentation reassembly 4944, and then we have frame delivery modes, how in the mesh network we deliver the frames in a multi-hop manner. So we have the 2 modes of mesh under and root over, again 4944. And the 2 last items are on fragment forwarding. So basically, in this item, we will present what are the issues that we have with traditional root over per hop fragmentation and reassembly. And once the students will understand the problem of the 4944, we will explain the latest standard 8930, how it somehow mitigates this problem in terms of latency and the reliability. And finally, in order to improve even more the network reliability, we have the 8931 RFC, which is on selective fragment recovery process. So again, we have all the text, so meaning the readings. We have the videos. So some of the videos are already online on YouTube, so feel free to have a look. We will have the quizzes and some exercises to calculate the compression level, for instance, or the efficiency actually of the compression and of the fragmentation. Again, we will have lab sessions based on 6LoWPAN networks. So where the IPv6 datagrams will be compressed and potentially, if necessary, well, in our case will be necessary so that you will play a little bit, they will be fragmented. So for your information, this week is almost ready. So we are missing minor items. And I believe when the time will arrive regarding my presentation on 26th of May, so this week will be available for the potential students to have a look. Actually, the whole MOOC will be available 1st of June, but this specific week, we are about to finish, maybe next week. We will complete our MOOC with week 4 and Ripple, so the routing protocol, the IPv6 routing protocol for low power and lossy networks. So where we will present series of standards. So the fundamental standard, the 6550, that represents the REPL, and then we have the standards on the two objective functions, the OF0 and Mr. Hoff. We will present the how the metrics are, what kind of metrics we have, and finally we will present the trickle timer algorithm. Again, we have the videos. Yet another video here is available, the readings, quizzes, and lab sessions based on Contiki. To conclude my my talk today, here I have one slide where I'm trying to do this mismatch between the IoT webinar series and the MOOC that we have here. So I'm trying to show you with the green color the matches that we have, and the red colors things that are not yet in the MOOC. So basically the introduction will be our week 0, the session 2, which will be presented by Pascal, if I'm not mistaken, the 60s. Architecture, well, as you can see here, we have the .NET and the raw architectures. However, in our MOOC, we will focus mainly on 60s architecture, as well as we will present the TSCH protocol, which is the protocol that 60s is based on. So the session 2 will be covered by the week 1 and week 2 of the MOOC. Then the most of the session 3 will be, well, almost the whole section 3 will be covered by the week 3. The session 4, which is related to REPL protocol, will have the week 4 on our side to cover it. However, we don't have yet considered the DAO projection and some of the RFCs, as you can see here. And finally, we are missing so far in this, but the door is open. Of course, it's time of, in terms of bandwidth and time to consider or not, to include the 6-loop neighbor discovery. So this is something that we are considering, but so far we did not find the time, or I think it will be done, but not for 1st of June. That's it from my side. So I will be happy to answer your questions if you have. So I'm trying to find how to close, to stop my session.
Thank you so much, Georgios. Thank you so much, Pascal. Was there anything you wanted to add here, Pascal?
Yes, Georgios, can you please go back to your last slide?
Sure.
the one which maps things. Yes. So yes, what I wanted to say is there was this question to which Rahul answered a little bit, or which was whether IPv6 was enough, or I guess was Michael asking. And on the chat, I answered there is IPv6 as an addressing scheme, right? And you can effectively address a lot of stuff. But then around IPv6 as an addressing scheme, there is also all the suite of protocols which come with it. For instance, ND, right? And effectively, we found in the course of the IoT work that ND, as was defined in the late 90s, was not fit for networks which effectively did not exist in those times. And so we, as Carsten said, we kind of redefined neighbor discovery and made a whole new version of it, which is completely compatible with IPv6 and augments the IPv6 architecture. But don't be surprised if in the future there is more need for evolution of IPv6 and augmentations of the capabilities without necessarily changing the address. Sometimes you may compress the address. Sometimes you may put semantics in the prefix. But it's not just the address, it's all those protocols that go around it, like ND. And so we brought this new 6-loop ND to the picture. And as you could see on Carsten's slide, in the IoT use case, we foresaw that this whiteboard, this registrar, where all the addresses are written, would be like this big box that is usually the ingress point to your wireless mesh or something. But IPv6 is a network abstraction. It's not necessarily, it's not just IoT. And as we designed this, we realized that hey, this new variation of ND can be ported on very different types of network where IPv6 plays. And effectively, we did. So we proposed 6LoWPAN-ND in a variety of environments where effectively the good old Slack is really not adapted. For instance, cloud. Very, very different from IoT, right? A cloud network. And yet 6LoWPAN-ND is probably the most optimal way of doing ND in that type of network because it doesn't require multicast. You get rid of MLD completely, which is a hassle, and true in IoT, but true on overlays in cloud as well. So you can see that things which were defined IoT are not necessarily confined IoT, and the concept and how we saw a 6LBR and this registrar IoT becomes the full BGP network in EVPN. So instead of being this whiteboard, this central box where everything is written, now it's a whole routing protocol which distributes the tables, and this distributed table is effectively the 6LBR. So small concept maybe, but effectively a great extension, a great capability to work throughout applications.
Thank you so much, Pascal. We have a question in the Q&A box, but I think it can be answered later because it's just about the logistics. Now, without holding any more of Shwetha's time, I'd like to thank you both, Pascal and Georgios, again for sparing your time and being with us today. This was indeed a very interesting session, and we are really looking forward to MOOC. And now the next session is actually, and this is also a final session for the day, so please stay excited. And this is something which interestingly keeps me up at night till now. And it's nothing but IoT deployments. And we have Shwetha moderating the session for us. Shwetha currently serves as the Ietf Ops and IoT Directorate. And she's a principal engineer at ThoughtSpot, and she works on securing the application and the cloud infrastructure. Shwetha has been an active contributor at the Ietf since 2008. She currently co-authors in situ OM related work, attestation related work in the RATS working group at the Ietf, and also chairs the 6LO working group. So Shwetha, off to you. This is your panel, so I'll leave it up to you to introduce the panel as well.
Thanks, Praneet. So we have thanks everyone for staying up, and thanks for all the speakers on such an interesting set of discussions so far. We have already been introduced to Carsten, Pascal, and Georgios in the last couple of talks. Let me introduce the new speakers who are going to join us on this panel. First, we have Rahul Jadhav, who is a long-term IETF contributor in the IoT focus work groups such as 6LO, ROAL, and LVIC. He's also a avid coder and contributor to open source code, including Linux kernel. Currently, he's VP of Engineering at Equinox, which he co-founded, and working in the space of zero trust security for runtime Kubernetes platform, building it out as well as evangelizing open source projects such as Bormann, which I have found it very interesting, and I'm sure anybody working in the K8 space wanting to secure it should give it a try. Welcome, Rahul. I will hear a lot about security, cloud, and edge and how it is playing a role in the IoT deployments from you shortly. Then we have Ravi Shankar Shiroor, Ravi, who is COO and co-founder of agri-tech startup Stella Apps. Stella Apps has been in news, has been doing some amazing work in the dairy supply chain, making use of IT technologies. They have been recently into pre-Series C funding, and they're on a mission to solve problems in the agri-tech sector and enable our farmers into becoming agri-entrepreneurs. Thanks, Ravi, for taking the time. We'll hear more about agri-tech and IoT deployments that Stella app has enabled and the challenges you have faced. Next, we have Sundar Ramakrishna. Sundar is is a serial entrepreneur. He has created 2 startups, and he has a breadth of knowledge in the industry. He's an ex-Cisco, worked in networking and security in a variety of companies. He's now he's the co-founder of Pinaka Software, which works in the defense and aerospace space, and he's working closely with Indian defense R&D organization, as well as private sector aerospace companies such as HAL, BEL, and Tata Group. He also founded a startup called Sharanga, which is, I hope I said it right, Sundar. So which built securing and managing platform for highly scalable IoT systems. And in his spare time, I'm hearing that he's building autonomous drones, which is more of an offense than defense technology. And we would love to hear all about how IoT technology is making a difference in aerospace and defense, and what Sharanga did shortly from Sundar. With that said, how we want to structure this panel discussion is first hear about the challenges faced in the IoT deployments and how each of our panelists have helped in solving them, and then move on to questions related or discussion related to what the future holds, and what we as the attendees of this session can help focus on and contribute the focus areas and contributions that we can be motivated to from our panelists. With that, over to Sundar to help us understand how does the IoT deployments help in defense and aerospace, as well as a little bit about the platform you built in securing and managing IoT deployments with Sharanga. Sundar.
Hey, thanks for having me here, Shwetha. For some reason, I'm not able to bring my camera up. I don't know what is going on, so I'll leave it as is. Anyway, you know for sure that I don't have a very interesting face, so we can discuss that later. Interesting question around military applications, which is what you introduced me for. So if you look at military applications for IoT, there are obviously many use cases which are pretty much of use even in civil applications. Things like asset management, predictive maintenance, fleet management, etc. But more and more, there is a willingness to deploy IoT solutions for core military applications, things like situational awareness or battlefield tactical reconnaissance. And these make for some really interesting deployment scenarios. Naturally enough, when it comes to when we move away from the core applications, there are some recurring concerns from military users, which are primarily of twofold. First is about scale. The multitude of sensors and actuators they'll be deploying, the multiple types of sensors being deployed, things like being able to assign roles to devices, knowing the location of devices that have been deployed, especially where there is high mobility applications, being able to quickly build and tear down ad hoc networks, and so on and so forth. So the scale of deployment in the user's mind translates to difficulty of management, and that presents an opportunity. The second cause of concern expressed by military users, of course, is about security. These two things are tightly tied. To a large extent, however, many of the old factors holding back deployments are slowly going away. Things like the fear of insufficient authentication and authorization, fear of insufficient transport encryption or insecure cloud interface, insecure device interface, and so on and so forth. I think there's more openness amongst the user community on these fronts, essentially because there's an acceptance that these concerns have been or are being addressed adequately by the underlying technology. So let me point out a few security concerns for military deployments that I have not heard very often from civilian deployment use cases. Again, it does not mean that these are not concerns in civilian deployment use cases. It's just that maybe the way in which military applications prioritize these aspects of security is slightly different. The first of these is around what we may call confidentiality protection. This is required for all communication channels, as well as data stored and processed both at the end nodes and the backend systems. Integrity is the second critical element very often we hear about, because it's important that information delivered to the command and control center by smart devices has not been modified and remains trustworthy. And another important element that I keep hearing about is about availability. The IoT in military environments can only be achieved if required availability of information is delivered from the sensors and devices and can be assured. And similarly, information from command and control centers should be available to the actuators and smart devices when required. So users are especially afraid of things like sleep deprivation attacks, where battery-powered devices are attacked and such that these devices are prevented from entering its energy-saving mode. So there are aspects of security which are kind of slightly different from what you hear in normal civilian applications. So these two present a lot of opportunity, and that presents for some interesting use cases and deployment technologies to be developed.
Thank you, Sundar. A bit about the security and management platform that Sharanga built?
Yeah, so effectively, in terms of management, it is centered around the ability to build ad hoc networks. Some of you may be familiar with Cisco had this technology which has been an Ietf for some time now called Autonomic Networking. So we tried doing something similar for constrained devices, where devices are able to automatically join a network, be auto-configured, be able to assign roles automatically based on certain conditions, and so on and so forth. So that contributed to the management element. And like I explained just now, the security element was focused on items which others have not quite prioritized. And we took care of things like availability, confidentiality protection, and integrity of data.
Thank you, Sundar. So the next one is to Ravi. Ravi, can you give us a little bit about the IoT deployment challenges that you faced when you started Stella apps, how the things have evolved over last 8 years, and what still exists? What are the problems you continue to tackle in terms of lack of standardization or regulation? So what does what next for Stella apps?
So, good evening, good morning, as it is applicable. So we at Stella Apps, we started about 11 years back. We did not know that we would work in agri-tech or in a dairy kind of environment. We just knew when we started the startup, we just knew that we wanted to apply M2M as a theme to whatever solution that we're building. It was called as M2M back then, and now it is IoT. Being a telecom engineer, we wanted to use IoT as a theme for the solution that we're building. And being a startup, being new to entrepreneurship, we did not know which sector to go behind. One of our friends was starting a dairy farm. He wanted our help in monitoring the dairy farm, how the person he's employing, is he following the protocols that are set, etc. So we thought maybe we could try that using IoT as a technology. It fit very neatly into the theme that we are thinking about. So we wanted to stick some sensors into the milking machine and into the biogas system and the cleaning system, cold chain, and all that. So we wanted to stick some sensors in the farm and get some data and give it to our friend to monitor his farm. And that's when the dairy sector the size of the dairy sector was started opening up in front of our eyes. India is the #1 milk producer in the world. We have about 550 million cattle in the country. The productivity is very low, though. So we are one of the biggest greenhouse gas emitters from cattle. Since the productivity per cattle is very low and it's situated in very rural areas, and on an average, the farmer is a very poor farmer. And on average, farmer has 2 to 3 cattle. That's it. So the affordability of the technology interventions is also very low. So although we were a large milk producer, the technology intervention was very less. We slowly started deploying sensors in the farms that you can see here for various purposes. One is the cattle healthcare tracking, heat monitoring of the cattle so that the productivity can be higher, and also for the cold chain monitoring of the milk, because milk being a perishable item is prone to getting spoiled. So cold chain monitoring and informing the users on the right time. So we started deploying these solutions. You can see in the picture. We didn't face too many issues on the standardization front. The issues we faced mostly were on the infrastructure side. Where do we get the power supply for our gateway from? How do I handle the deployments in a muddy kind of environment where a buffalo would go and sit, what do I do when the network coverage is very low? When we started, it was mostly 2G and 3G. 3G was just starting off. 4G was not even there. So how do we manage a network that is just fading in and fading out? Once in a while, you just get a little bit of a 4G network. So that kind of challenges we had faced. And even now, I wouldn't very confidently say that we have very good coverage all over the country. Even now, half the villages are still in 2G, and even in 4G, only some of them are IPv6, and some of them are not still supporting IPv6. You could see in this picture, on the bottom left-hand side and on the bottom right-hand side. So you can see a small pipe that is tied to a tree, or pipe that is put on a wall. So that is basically our gateway. It has a 4G SIM inside or a 2G SIM inside, and we need to collect the data from the sensors in and around in that village. We use 6LoWPAN on our devices mostly, and we run COAP on top of it. And because of the IPv6 issues, we had to, we still have to use tunneling over V4 sometimes to get the data to the cloud and so on. SIM management was an issue and continues to be an issue as well in our deployment. Standardization perspective, not too many things. Mostly, it served our purposes. Infrastructure has been our main limiter at the moment.
Thank you, Ravi. That was very insightful and kind of opened us up to the real world problems.
Yeah, you can also see a solar panel there. I mean, just because we don't get power supply that easily, right? You can see in the background solar panel mounted on the top of the hut or by the side of the tree to get the power to our gateways as well. Yeah, sorry, go on.
No, thanks, Ravi. We would also like to hear about what are the other than the infrastructure, what new innovations and challenges lie ahead in this vertical. But before that, maybe we can hear about security, cloud, and edge, and from Rahul, and how they are playing a role in easing or expanding the IoT deployments. Rahul, over to you.
Yeah, thank you, Shwetha. Maybe I'll just give a quick background about because we're talking about IETF and standardization, and some of the problem statements that we faced while designing our solution, and what role did IETF play. I would like to talk about that before jumping into other topics. The problem statement that we were tackling was deployment of smart meter solutions, and we found that this was a problem statement that the business group brought to our solutions team, and they said that, is it possible for you guys to scale to 200 or 500 nodes? The moment they say that it's possible to do simulation and check whether you can actually scale. But in real world, whether it is possible to scale or not, we really don't know. Simulation doesn't work, may not necessarily work in the real world. So when we actually started deploying the hardware-based sensors, we found that there were a lot of things which we had to work upon, and we thought that maybe it may not necessarily be true that we would be the first to solve these kind of issues. And that's where that's where we we thought maybe let's ask the experts. And that's where we first floated the problem statement draft in role working group, specifying the problems that we are facing and whether it is a problem that everyone faces, or whether it is a one-off problem. We got very nice reception. Michael Richardson, Pascal, everyone just threw in all their weight trying to explain what others have been doing in the context. Then once it was agreed that this is a problem statement to some extent. Not all the aspects of problem statements were true, but at least some aspects of the problem statement were true. Then we decided on the solutioning perspective that we had something in mind. The journey from the problem statement, looking at the problem statement, facing the problem statement yourself, going to Ietf, asking the experts, and then designing a solution around it, and then seeing that solution standardized was an experience in itself. It took few years to finally get things standardized, but it was totally worth it. The way in which the Ietf body works, it was quite a revelation for me. It's not like I've been a long-term contributor to Ietf, but certainly discussing with the experts helped a lot.
In terms of security, I know at Equinox you are working on zero trust security. Does that apply to the IoT networks as well?
Yes. So at Equinox, what we're trying to do is, you have edge devices, you have IoT devices, and one is, of course, providing an identity to an IoT devices, which essentially means provisioning credentials. How do you do that? Once you do that, how do you scale that identity and use it subsequently for authorization purpose? All these are new elements, not necessarily new elements, but to scale to the level of IoT problems is something that we are trying to build on. One specific example is that the IoT devices, these are prone to attacks, right? They are out there in the open world. You have physical. It is possible that the attacker might have physical direct contact with the IoT device. It becomes more and more, so one of the problem statement that we have been dealing is it possible for us to limit what the IoT device can do? Use things such as zero trust, which is essentially a new security architecture that NIST has been proposing and has been actively advocating. We thought, is it possible for us to bring that to IoT and edge devices? How do you auto-generate policies? How do you enforce those policies at the IoT devices? Again, I won't say all these are solved problems today, but these are some of the problems that we are attempting to solve.
Thank you, Rahul. Now over to Carsten and Georgios for first Carsten. So I know you've been a big contributor. We heard such in-depth, in such a short time in the first presentation, how you shared the details about how idea of IoT has evolved. Would like to hear from you on how, as an academic, you have built or you have contributed to the IoT stack, learning about the IoT deployments, which probably would have been in very early stages when the IoT effort within Ietf started. For example, how did you conceive protocols like co-op? How did you learn from the industry on the challenges that IoT deployments may face in future? How did you do that?
Yeah, that's actually a very good question. A question that many academics face. How do you actually find out what the pressing problems out there are? And sometimes it's really hard to find people who know that and who are actually prepared to share that information. And it turns out that the Ietf actually is an amazing organization for finding these people, because you find a lot of world-class engineers, but you also find contacts to other organizations that work in that space and that want to get things going in that space. And for CoAP, for example, one such organization was the company that was running a combined industry and research project. The EU has a lot of these projects, and the EU project Sensei actually had pioneered some of the ideas that then went into CoAP. But really, my contribution to CoAP was not that much designing that protocol, but asking the right questions. And then finding those world-class engineers who actually are interested in contributing to this and running a working group process that actually yields those designs, and things that don't work get discarded and other things get added until you have a protocol that actually solves the problem of the actual industry people who are out there trying to use this.
What would you advise to some of the academics who are here in the attendees on what to look for, what kind of open source projects or standardization efforts to follow to do something similar to help evolve IoT?
Well, that's not an easy question. That's really much of the reason we are running institutes like the one at my university, the TZI, that actually tries to bring researchers and industry players together. So it's really helpful to have an infrastructure that helps you with that. But of course, there are people out there who actually do try to communicate their observations. Sometimes you have to be a little bit careful, because some of these interesting blogs you might find actually are from people who are trying to peddle the new products of their startups and so on. But in general, you can learn a lot from people who actually have been in the trenches and trying to get things going, and can describe what their actual pain points were.
Thank you, Carsten. Georgios, similar question to you. You've done a lot of research in the industrial IoT areas. What kind of challenges that you continue to face in the industrial IoT deployments, which keeps you up and motivated to do more research?
Thank you so much for your question. So we'll give you the example that we have been working on since 2017. So basically, we are working on a wireless battery management system in electrical vehicles. So the idea is that we have the BMS, the battery management system, which is a critical system in charge of monitoring the battery cells, voltage and temperature to ensure the smooth operation in the vehicle. So in a wireless BMS, the idea is to replace these wired URT cables with wireless communication. And according to our industrial, automobile industrial actually partner, the WBMS, the wireless BMS, brings several benefits for them, like simpler battery second life management, easier fabrication, and fewer connection risks. So working on this, towards this project, we had to deal with a challenge, which is on how to have an efficient scheduling and resource allocation algorithms in order to achieve ultra high reliability and bounded latency, and of course, low energy consumption. So the idea is that the BMS composes of the master and several slave nodes. And the idea is that these slave nodes transmit the information regarding the consumption and the temperature actually the cell voltage every 100 millisecond or 150 millisecond to the master. So this is the problem for the bounding latency. So we have to guarantee that we have this reliable communication non-stop within this 100 millisecond loop. So we had several issues there, how to have this, how to create this schedule and how to achieve to have reliable, because if one frame doesn't arrive, we need to consider to have some cells allocated for retransmission and so on and so on. So this was the first challenge. And the second challenge was how to keep the synchronization and the cell balancing of such electrical vehicles. So I'm talking about mainly French automobile industry. Yeah? When the vehicle is turned off, so when the vehicle is parked, so which means that we are in sleep mode. So the battery management system should go to sleep mode. So the idea is we have to maintain the cell balancing and to keep the network synchronization. So here we have the problem, which is the master of the WBMS must stay active mode, which discharges the actual small 12-volt battery of the car. So we had to find some solutions on how to guarantee this requirement as well. So you see that even though we have been working, well, I'm much younger than Carsten and Pascal, working more than 10, 15 years, we still have the problems today in a new industrial use case, such as the electrical vehicles.
Thank you, Georgios. I think that was very interesting examples to think about, and I'm sure some of the things that Pascal has been doing in the 6-star deterministic networking area would be very applicable in this space as well, and also in the lower layers, in the physical layers and the wireless area. These are some of the problems that we all can contribute to. So Pascal, we would like to hear about all the complex challenges that we face in 6-star deterministic networking and RAW that you're working on, and how those are applied in real world deployments, and what kind of additional challenges you faced when deploying these frameworks, technologies that we have been building at Ietf. I know you have a lot of experience in innovating at Cisco in the mobile and wireless space. So any examples that you can talk about that will help us get a picture of this will be very helpful.
Well, what I could do is give you two very different categories of examples. One of them being already deployed and I would say successful for this case of 6-stage. So 6-stage, like I said, is an architecture and basically a proof of concept that we can effectively build a device that implements the stack of Ietf components. Now, when you go to the real world, there will be alliances that will take some or all of those components, and I'm thinking about YSUN, thread, etc., and we'll build their own solution by nitty-picking exactly what they want from all those RFCs. So basically, the 6-stage architecture makes life easier for them to assemble those things because we kind of did it ahead of time and we can show how that can be done. One successful real-world application of that is effectively YSUN for the smart grid. So YSUN is a standard that looks, in terms of architecture, very, very much like 6-stage. They have a slightly different lower MAC. So they don't effectively use TSCH as is from 8.15.4. And one reason is that they are using a very wide area radio. I mean, they're using the sub-gig 15.4. And they have a lot of contention. So they basically cannot allocate time slots exactly like 6-stage wants them. They want to have longer time slots and the minimum of collision avoidance in those long slots. Also, that reduces their need to synchronize. So there are different MAC, but above that, it's 6LoWPAN-ND, 6LoWPAN-HC, it's repo, it's all those nice co-app. It's not just all those nice things that we've been discussing about. And so the application of Wysen it's an alliance that's very dedicated to smart grid. So what we do is we build products that are like your electrical meters, and they will build large meshes between houses to the report route, basically, and report metrics, and you can also send data to the meters, etc. And so there are, in North America, there are millions of devices which are deployed like that, and each ripple mesh is typically several thousands of devices. And so you realize that if you wanted to do networks of this size on Ethernet with classical ND, it would explode. And we managed to build network subnets of that size over thousands, sometimes tens of thousands devices with low power, highly constrained devices, and still it holds. So that tells you that from the early days of IPv6, some evolution has taken place, which effectively you can build what you want, making the right effort. And the 6-dish architecture was exactly that effort. Now, my own interest in 6-dish did not start because of smart grid. It started because in the mid-2000s, I was working at an industrial standard for process control, which was called ISA 100.11a. And that standard, I knew nothing about it when I joined, like in 2005 or something. I was just asked to help the standard adopt IPv6. I'm like, Carsten, IP where it's not gone before. And so try to see how an industrial standard for process control could effectively be using IPv6. IP, and it happened that it could only be IPv6 for the reason I gave. And that's when I got caught in, the industrial operation technology type of use cases. And all the work that came since for .NET and RAW, my contribution came, from those days where I started working with those guys, discovering their problems. And effectively, it kind of boils down to what Georgios have been telling us, that you need to deliver reliably your packet with a bounded latency every time. If you have a control loop in an industrial process, like manufacturing something, or in an automation, like self-driving a car, typically you need a packet assistant period. It can be 100 milliseconds, it can be a portion of a millisecond. And you need your packet with a very, very strict jitter. So the latency has to be this with very, very little chance. If your delivery is not at the right time, the control loop may lose stability and your process may go to hell. And so basically the idea is in a control loop, if you lose like 3-4 packets in a row, the system will go in emergency stop. If your devices do that once a year, the factory will look at you with very bad eyes. If you do it twice in a year, your hardware will be on the curve. So it's very, very important and very challenging in radios to be able to deliver reliably packets every time. Sometimes it's safety, sometimes it's life at stake, right? So this is the kind of criteria. And that's why we did .NET for wired and extended it with RAW for wireless, because RAW brings the additional constraints that I discussed earlier on my slides. And for RAW, we extend the capabilities for diversity. So that's why, you see all this chain of work, starting at 6-dish, which was the first deterministic radio to .NET and RAW.
And I also see that you're continuing to bring additional interesting work in 6LoW as well for improving the addressing and registration of the addresses, which would make it better for both IoT and otherwise as well. Thanks for doing that, Pascal. Since I think we are on time now, Dhruv, if anyone has questions, please post it in the Q&A or raise hand, and we can ask our panelists their opinions and thoughts on what you want to hear from them. Since we do not have any questions yet, I just want to hear about patents and how that influences IoT deployments in a proprietary or standardized way. We can start with Pascal, because Pascal has like 300 plus patents, which is like amazing, and some of them are in the area of IoT. So how does it hinder or help in IoT deployments, a standardized IoT deployment, especially for startups like what Ravi spoke about, the Stella app startups, or or work that Sundar is doing, how does it have an impact? Does it hinder the IoT deployments?
Okay, so yeah, that's a very interesting question, Shwetha. And well, there are all sorts of companies which have all sorts of policies for their IPR, and I'm in a company which uses IPR as a defensive method. And if you remember the world, you've been there, so you know that it's hard to live without some protection in that kind of world. But anyway, for most of the things I've been doing at the Ietf, I try to actually avoid encumbrance. For instance, we talked about 6LoopND. I have no patent on 6LoopND, not at all. And it was really, I really wanted to make sure I did not, and that doesn't change the fact that for the most piece outside of the IoT, it's very hard to get any adoption. So the patents were not at all an hindrance, because it's not being adopted, it's not because of patents. At the same time, I have like 10 foundational patents on REPL, and that has not hindered adoption, open source implementation, etc. For the most piece, if you have a standard at the IETF, you'll find that when there is IPR, there are run terms associated to that. So if you're writing code and for your products, but you never intend to attack the owner of this IPR, normally it's usually free. It's actually free, actually. And with Cisco IPR, it's free. So it's never been an hindrance for anything. For instance, I have the patent for 464xlat. You have a phone. Probably you're infringing my patent. Did that bother you anytime? No. So basically never hindered anything to my best knowledge. And the lack of patents was never helping a lot, progressing things like 6LoopND outside of IoT. Did not change it. So I don't have a very bad experience about patent. Oh yeah, I have one. I had an interesting technology for doing mobile IP over IPv4, so mobile IPv6 over IPv4. It would go through any form of NAT, actually reverse NAT, etc., which the technologies of the day could not do, like Teredo or something. And it was really, the trick was to couple the encapsulation with the mobility protocol, so that would effectively maintain things active, etc. So it was working fine. I had my prototypes, was happy. Proposed that to the ATF, and the chair of the day said, I don't want, just a chair decision, said I don't want a draft which is encumbered in my group. And so that proposal was not discussed. And actually there was nothing to match it since then. And so the only time where I was bothered for anything IPR was effectively by IETF itself, by one chair who had that policy in his group. But never by the products, never by the competitors, never nothing. So
thank you. Thank you, Pascal. So, I mean, last 3 minutes, perhaps, in very short, can Ravi, Sundar, Rahul share about what would you like this community here to focus on in the near term to help in the IoT deployments and IoT technology that you have seen from your experience in different verticals? Ravi?
The top of my mind recall is the mesh network. We have started trying mesh architecture in our deployments. If there are any gaps in mesh, I would request that to be filled. Second thing, probably more open source, with some of these standards implemented, more choices. Sometimes we don't have too many choices. We have to pick up a certain source. We have built our entire stack based on open source. Sometimes we have lesser choice. So more choices on the open source will be helpful.
Thank you. Sundar?
Yeah, so just last week, Shwetha, you and I were discussing some news from the unfortunate conflict currently underway in Europe about the use of drones to gather information on movement of enemy vehicles and using Starlink-delivered internet connectivity to provide location and movement information to their artillery systems. So I think this kind of deployments are going to be more and more prevalent. The usage of drone-mounted sensors connected via a satellite-enabled internet to provide real-time actionable information is going to be real. But the challenges are also real. Making satellite-based IoT work, and it requires a lot of overcoming of some limitations in 5G technologies. I don't know whether it's Ietf per se, but a major evolution of 5G is about the integration of geostationary and low Earth orbit satellites with terrestrial systems. And from what I hear, seamless integration of satellites to terrestrial mobile networks requires significant adaptations, primarily because the 5G control and data plane has been standardized to handle only continuous backhaul communication between the network components. A mobile or a UAV-based or satellite-enabled Node B platforms need to be able to handle frequent backhaul outages of various durations, as well as longer signal delays. So I think exciting times ahead, but we need to be able to adapt satellite-delivered 5G services for IoT.
Thanks, Sundar. Yes, that's a very also the evil use of IoT. For example, what you see in this slide is the Black Mirror episode where the autonomous drones are used to attack humans, which was very interesting as well. Rahul, what do you think? What is top of your mind that we can look into, focus on in the coming years?
Yeah, I've been part of the mesh protocol standardization, the Ripple working group, and I can see that there are a lot of problem statements out there still yet to be resolved, and there's certainly a lot of scope for experimentation and bringing out the right solutions out there. That is something that I feel that over a period of time, and some of the solutions out there like Google Thread are trying to handle some of the problem statements in a very different way. But yeah, mesh architectures like Ravi mentioned, it continues to remain a big problem. The second point is the security. I know everyone talks about security, but if an organization has not taken into account the security aspect of things for an IoT deployment, I mean, I'm pretty much sure that all the assumptions are going to go for a toss in terms of performance and scalability. I've been there multiple times, and every time that happens, it just bothers me as to how much of areas are still unexplored. So yeah, those are the two. And Ravi also mentioned about open sources. Having a good open source, having a nice implementation of a protocol which can scale, which can perform well, makes a world of difference. Even in our case, when we started out building our product, we found that some of the open sources can't be directly relied upon, and then we had to build a lot of things by ourselves, and we started contributing upstream towards those open sources as well to make it more effective. But yeah, open source is also a major point I would say to look for the future.
Thank you. I see there is a Drew. Did you see someone raising hand? Was it Mike?
Mike, you can go ahead and answer.
Yeah, I have been raising my hand. Great stuff, everybody. I think this is a question for Pascal, but there was a couple of your slides that basically said that IPv4 was bad and IPv6 is wonderful, which I agree with, by the way. And what I was going to ask about is you had a list of advantages of IPv6. One of them was ND. Can you elaborate on why ND is an advantage? And I'm assuming that's geared towards the new ND for 6LoWPAN, and probably some of that is multicast at least. But what else? And then here's my real killer question: is could that new ND be used in non-constrained networks as well? So I hope that makes sense.
You missed the time when I said it, Dhruv, but I effectively mentioned that. So you're completely correct. I mean, the legacy Slack is even worse than ARP when used in a network where multicast is not welcome. So the key thing is effectively the 6LoWPAN ND that we have defined at 6LoWPAN and extended at 6Low. This one gets rid of most multicast and avoids MLD completely. So this is a huge advantage for IPv6, because basically what you end up getting is a link model where you can effectively decouple the layer 2 construct, which is what we call a subnet or a segment, from the layer 3 construct of an IP link and an IP subnet. So they're completely decoupled. For instance, if you have a mesh of wired or wireless, you can decide that you form your IP links as being point-to-point between hosts and routers, and then routers and other routers, and do all your IP like we do in 6LoWPAN and REPL, with what we call rotover. And that you can do that on a wired or wireless mesh, and really you don't care anymore about what the broadcast domain is. On wires, you could say your broadcast domain is this Ethernet fabric, but on wireless, unless you have a multicast emulation like the BSS and the ESS in Wi-Fi, the broadcast domain doesn't match what you would like it to be. So having the capability to do a layer 3 that is your own construct is a huge power. So basically, that's the enabler of that is 6LoWPAN, creating those links where you want them for IP, regardless of the broadcast domain below. Whether I can see 10 nodes or 100 or just 2, I will build those links that I care and ignore the rest. I will decide that those 1,000 devices are in the same subnet, regardless of the layer 2 connectivity, which could be 10 of them. You can't do any of that with IPv4. So yes, ND is 6LoWPAN ND is very big. And to your other question, we already redistribute 6LoWPAN ND in REPL, obviously, because that's what it was meant for with the 6-dish architecture. We also redistribute it for ND proxy, and that enables to have a state for ND proxy, which is a deterministic state, very solid, compared to what you would do with ARP, snooping ARP or snooping DHCP. And even worse, snooping Slack is really unreliable. We can, Yes, we can redistribute in Rift, which is a new routing protocol for data center that inherits from REPL, by the way, as well, because like REPL, it is anisotropic. It has a sense of direction. One very big novelty in REPL is, there is a sense of north and south, up and down. And you don't route the same way. You don't do the same operation up and down. That allows you to save a lot of energy state, etc. So yes, it's redistributed in Rift. And I have this draft in EVPN. And the interesting thing in all those drafts is the concept of 6LBR shows really as a logical concept. It can be a box, it can be a database with a lot of synchronized nodes, etc. It can also be completely distributed by ND, for instance, when it's a backbone router, when it's proxy, and then the state is effectively distributed. Each 6LBR connected to this backbone has a portion of the whole set of addresses in the subnet that is federated by that backbone. So it's a really distributed table. It's a collection of 6LBR, each one with a portion, its own LLM, if you like. But using ND over the backbone, they can see if the address already exists somewhere else. Just do lookup. And if there is no response, yes, this address is free, you can respond OK to your own LLM. That's how you do ND proxy. But when you redistribute in EVPN, which is a BGP routing protocol that's meant for data center overlay, what you will do is synchronize completely the state of all those local 6LBRs. And so really the BGP protocol itself becomes the synchronization protocol for the 6LBR. And the 6LBR is a logical entity which is in every node synchronized with all the others with the sum of all knowledge. So you can see there are tons of ways. And then there is Lisp. Obviously, Lisp is the equivalent of the Dardak that Carsten had on his slide. So with 6LoWPAN ND, we have effectively an ND model that can be implemented by BGP and can be implemented by Lisp. And for the host, it's always the same model. You don't know, you don't care how the backend does that. So you're completely abstract on the IoT devices, which has this little tiny code to how you do the routing in your backend, whether it's EVPN or it's REPL or it's ND proxy or whatever else. You have this completely abstract host to router interface where the host can just say, hey, I've got this address. Please do whatever you do to get the packets back to me to get my address reachable. That's a huge power that only exists in that space.
Thanks, Pascal. I think Mike,
let me just say your answer.
Go ahead, Mike.
I was just saying thank you. Your answer exceeded all expectations. I missed one thing. You have a draft regarding this in what working group?
Oh, BESS. The group is BESS, BESS, and that's the group that does EVPN, which is basically how you use BGP to advertise certain types of route, in particular type 5, which is associating an IP and a MAC, so that you can build an overlay.
That is great. Thank you so much for that wonderful answer.
So thank you, everyone. I think we are way over time, and Dhruv has been sending me direct messages to wrap it up. So while I would love to continue this chat and have more questions, I think it's time we call it a day. And thank you so much to all the panelists for taking the time and sharing such insightful thoughts with all our attendees. And thank you all the attendees for staying back, though we ran over time. I hope you found this discussion useful. Dhruv, back to you.
Thank you for having us here, Shwetha. Thank you so much.
Thank you so much, everyone.
Thank you.
Wonderful job, everybody.
Thank you so much, everyone. And now, before we end, I know that we have a curious audience here, and some of you might not have gotten the chance to ask your questions, but this is not over yet. We have a lot of channels through which you can connect. The main one being our WhatsApp group. And if you have elaborate questions, feel free to join our mailing list and send out your questions. All of us will be very happy to help you out there. And then we also have the LinkedIn and the Twitter handlers where you can connect and stay updated with our latest happenings. For INTC, you can become a member with the given link. We'll be sharing these slides so you can find the information in there. And we have a lot of interesting webinars and workshops happening with INTC, which should be very helpful to the audience. Finally, I would like to again thank all of you for choosing to spend your time with us today. And this wouldn't be possible without our speakers and the panelists. Thank you all again for joining us and making this happen. And finally, tomorrow we have the final day. This was the day 4 of the post Ietf 113 forum, where IoT was discussed at elaborate lengths. And it was a huge success to me, at least, and I hope you all enjoyed it too. Finally, tomorrow we have the day 5, and which is the final day, where we have the topic as Beyond Ietf, and we have some very, very interesting sessions for tomorrow as well. So please join and stay connected. Thank you, everyone.
Thank you, Praneet, for today's session. Thanks all speakers. See you tomorrow. Bye.